think so. We did this one. So everyone, welcome back. Things so just try to recorrect what we last left. Yeah, I had done this read after write consistency, and we were talking about the different devices where it has to manage uh, the time for that replication wise. I think so. We'll have to. We'll begin from the monotonic elements. Before we go ahead, guys, anybody has any questions, any queries from the previous one? Okay. So, all right. If there's no questions, so once again, guys, welcome. We are going ahead with monotonic reads, Mudasar. Okay, let's get started. Right. So, just to give some context before we jump there, we were talking about leader follower configurations. Then we're talking about certain challenges in the leader follower part and how do we address them one by one. Right, replication lag is what we were talking about, and there were various approaches being discussed. Sorry. Okay. Monotonic reads. Okay. A second example of an anomaly that can occur when reading asynchronous followers, that it is possible for a user to see things moving backwards in time. Okay. It's interesting. This can happen if a user makes several reads for different replicas. For example, in the figure, user 2345 is making the same query twice. First to a follower with a little lag, then to a follower with greater lag. Okay, this is the user. Okay, this is 2345. So this reads from the follower, and this is another follower. Okay. The sequence is that it first reads one follower with a little lag and then the other follower with the greater lag. This scenario is quite likely if the user refreshes a web page. Each request is routed to a random server. The first query returns a comment that was recently added by user 1234. But the second query does not return anything because the lagging follower has not yet picked up that write. In effect, the second query is observing the system at a particularly early point in time than the first query. This wouldn't be so bad if the first query hadn't returned anything, because user 2345 probably wouldn't know that user 12345 had recently added a comment. However, it's confusing for the user 2345 if they first see user 1234's comment appear and they see it disappear again. Just to summarize the problem statement here, guys, is that this user is trying to read and the request goes to the follower one, and then the second time when it reads for whatever reason it goes to the follower two. But in this process, what has happened that when the first time he got the data from follower one, he saw some data. It's, let's say in this case, the comment coming from user 1234. Okay, he saw that, but when the next time the request was made, he could not see that comment because the follower from which the read happened, it was lagging. It was not updated. So I hope the problem statement is clear to everyone. Okay, so hence we start talking about monotonic reads. Monotonic reads is a guarantee that this kind of anomaly does not happen. It's a lesser guarantee that strong consistency. Okay, it is a lesser guarantee than strong consistency, but a stronger guarantee than eventual consistency. This is something more consistent than eventual consistency that we saw. When you read data, you may see an old value. Monotonic reads only means that if one user makes several reads in a sequence, they will not see time go backward. That is, they will not read the older data, sorry, older data, they will not read the older data after having previously read newer data. Okay, so monitoring reads are going to address the problem. How? I don't know yet. One way of achieving the monitoring reads is to make sure that each user always makes their reads from the same replica. Yeah, that's one way of doing it, right? Right? Each user always makes their reads from the same replica. Different users can read from different replicas. For example, the replica can be chosen based on a hash of the user ID rather than randomly. However, if the replica fails, the user's queries will need to be rerouted to another replica. Okay, I think this is something I believe everybody must have got it right. The problem statement where the lag is happening for the second follower, update data is not coming. And monitoring reads is a concept introduced over here, which says that each user makes the read from the same replica.
Yeah, so the last statement, however, if that replica fails, the user queries will need to be rerouted to another replica. So in that case, it will still see some, in some cases, it will still find monotonic read issues, right?
Yeah, it will actually.
Okay.
So I think actually what I think they missed to say here is actually, so let's say there is one thing we can do here, right? Actually, every time we read something, we have to remember the server has to send us some identifier like the transaction ID or some ID, right? In the log actually. So next time when we get rerouted to a different replica, right, we always present that last read ID. So the replica where we are getting connected can see what is the last seen ID of that client, right? Then it can make sure that if that replica is not up to date till that ID, it can reject that request, or it can stall that read and say, actually, I'm not ready yet. Actually, you have to wait. That way you can avoid going back in time. Actually, that's what I'm thinking.
So I think, is it what you're talking about, stateful service about?
It's not stateful. The state is kept in the client, not in the server machines.
Server. Okay.
Yeah, because as a client, I remember what I did. If I crash, then I will lose that information. I have to store it in some persistent way in a disk or somewhere. But if that doesn't really matter, that's fine actually. If I crash, I come back, I read it again, and I remember the last point where I read it from.
Okay,
Now,
kind of.
yeah.
Yeah.
Yeah, this has the same issue we discussed last time also, right? If I'm reading from laptop and I'm going to check the same thing from the phone, I could be routed to different replica, and there is no connection between the last read in the phone and my laptop, right? Yeah, that could still happen.
Similar, but yeah, makes sense.
But that is based on user ID, no? Like user ID will be same either you use laptop or phone, correct?
But actually, yeah, that is fine, right? When I read it from my laptop, my session, so the laptop only stores that information, right? It is not stored in the session associated. Sorry, it's not stored in the server, right? Associated with my
Correct.
session. Yeah, that's the problem. When I log in from the phone, actually, that information is missing. Actually, phone client sees that I'm doing a fresh call, right, to read that.
Yeah.
Yeah.
Okay, that's cool. Yeah, I mean, with regards to backups, I think so. We have seen aspects like maintaining a certain log, which can be referred to the latest, if it is reading the older value or not, or maintaining certain incremental identification, so that next time when it is reading, it knows that it has to read something in addition to what it read last time, rather than the older one. That was something I think we saw in LSM. I don't remember, can't recall.
Yeah.
Not sure if that would apply here though.
Actually, a lot of those systems, right? Actually, that's why this kind of consistency is kind of hard to give, right, across the multiple devices of the client. So I don't know how other systems do that. this is actually more stricter than the read your write consistency. Read your write consistency, they only guarantee that I will read my last write, right? Here they are guaranteeing that actually I will see everything I saw already. Kind of situation in linearizability or the real-time situation, right? If I see something already, then the system has to make sure that I don't see go back in time. Any idea how we can achieve this? Actually, that's what I'm thinking. Yeah, probably we can continue and see maybe the answer is somewhere there.
I think they might be able to use the vector clock. The vector clock will have the ID along with the like increment ID to determine what message happened first and which one happened second.
Oh, you're saying using a vector clock or version vector, something that.
Yeah.
Is that not used for a conflict resolution? But this is not conflict resolution, right?
Yeah.
I don't
Right.
know.
But it's still like it will help us to identify which one happened first and which one happened. It's kind of sequential, right?
Okay. So some ordering you mean to say, okay.
Yeah.
Yeah, so first think like that, okay, in what scenario this problem will happen? So this will happen only when we have async replicas. If all the replicas are synced, so that will not happen.
Yeah, that's correct. Yeah.
So if it happens in, okay, so now in async replicas, so the problem is that when you make a request, first time make a request, and let's say it go to one async replica. Second time you make either fetch the same information again. So now this time system decide and redirect to the different async replica. And these async replicas are not, I mean, they may have different location or different checkpoints. So one way is author mentioned here in this, you guys already read that. One way is that stick with the particular replica. So always for a particular client, always redirect to the same replica. So that problem will solve in that case. This problem does not talk about that how up to date the information will be, but it talks about that when you get the information once, you will not read the old information or older than that. It does not, this problem does not say that, okay, this is, you will always get the up-to-date information.
Yeah, I agree, right? Actually, let's say the replica I'm reading from crashes, right? That's where the whole problem is, right? I will be redirected to a different replica.
Yeah, so if redirected to a different replica, so then the solution could be, so like client pass some information, as you mentioned that.
Yeah.
And in that case, either replica, two things may happen. One is that either replica, if replica is not up to that point, so it hold that and delay the response. And the second is replica immediately reply that, okay, I don't have anything. In that way, client will redirect to find the another replica for that.
Yeah.
Okay, so if you want to maintain that consistency, you'll have to do it. Okay. So
Yeah,
some requests will have some latency issues, but not all. Yeah. Okay.
Yeah, I mean, here, if we are talking about the client, so someone who actually, so like the library of your system running on your actual client side.
But in this case, the client does not know all the replica. Right? The client.
That's why I'm saying that. That's why I made it clear that if I'm saying that client, it's not someone actually like your application. Maybe your application uses some library that which actually interact with your backend system. For example, let's say if you are using a blob store like S3 in your application, and on your side, you are using a thick client of your blob service. So that thick client of your blob service know that how many replicas, where are those replicas. Anyhow, it will get the all this information from the server, and then it will go one by one. If one replica is not responding, then it will try to connect with the another replica.
The client library will be very smart and intelligent one.
Yes.
Yeah, but
Okay.
in this case, the replica, one replica is crashed, right? And then we make a request to the proxy that return you data from another replica, and you only know the data from that replica. You cannot go and query another replica to say, okay, they want to sync the data.
Yeah, but in that case, it will go to the server again because it is crashed. So it will go back to the server, and server will give it the latest information, and there might be some redirecting happening there.
Right, but it could redirect you to the replica that have old data, right? The next time you make another request, it redirect you to the to that replica again.
As you said, like you can hold the request or maybe do something else, send some different message.
There are multiple ways to implement that. Either your replica will hold and it will not reply back, or if it reply that I don't have the data, then you will make request to the another replica or another server.
Yeah, it might be depending based on your requirements. Yeah,
Zookeeper is similar to that, right?
Yeah, Zookeeper is doing the same thing. Yeah.
Chubby also does that. Yeah, you have that client, and the clients actually have those caches. And the caches are actually invalidated at the time. So you actually delete the cache again. So you will go back to the server to get all the information. Yep.
But actually, Zookeeper, I think their consistency model is a little bit relaxed than this. They're only guaranteeing read your writes consistency. They are not guaranteeing this monotonic reads.
No, they are monotonic itself. So they maintain that ZX ID.
Yeah,
whenever you are.
Yeah, so let's say you made any change, right? Yeah, I think so. Yeah, it's monotonic read. Yeah, so
monotonic reads. So whenever, even if it, so they are generally connected to one replica itself. Even if it reconnects to another replica due to network or something, they ensure that connection happens only if the ZX ID is at least as recent as the ZX ID received from the client.
Yeah, exactly. Yeah. So somewhere I wrote actually they provide this read your write consistency, but I think it's the same thing. Monotonic reads is pretty much the same thing. Yeah. Yeah, just only question I have is actually, yeah, the ZXID is, if ZXID is there, actually they will make sure that actually I will see any data up to that ZXID. Okay, that's good. We can continue. Yeah.
Yeah, but this is a really interesting problem, right? It looks so easy. It's not that easy to solve.
Yeah.
Okay. Yeah. Let's go ahead.
Yeah. All right. So that's monotonic reads. Moving ahead. Consistent prefix reads. A third example of replication lag anomalies concerns the violation of causality. Yeah. Imagine the following short dialogue with Mr. Poons and Mrs. Cake. Okay. Okay. Sorry. Yeah. Mr. Poons, how far into the future can you see? Mrs. Cake. Mrs. Cake, about 10 seconds usually. Mr. Poons. There's a casual dependency between these two sentences. Mrs. Cake heard Mr. Poons' question and answered it. Okay, that's interesting. How far into the future can you see? For 10 seconds usually. It's casual dependency between the two. Because Mrs. Cake heard Mr. Poon's question and answered it. Interesting. Now imagine a third person is listening to this conversation through followers. The things said by Mrs. Cake go through a follower with a little lag, but the things said by Mr. Poons have a longer replication lag. This observer would hear the following. Mrs. Cake, about 10 seconds usually, Mr. Poons. and then Mr. Poon saying how far into Mrs. Cake. To the observer, it looks like Mrs. Cake is answering the question before Mr. Poons had asked it. Such psychic powers are impressive but very confusing. Okay. Okay. We have an interesting diagram over here, which yet has to be elaborated.
So it's like WhatsApp chat, right? Looks like, I mean, two members are talking, right? Somebody's message. I mean, that has to be ordered, right? First followed by the second. But let's say somebody asks, how are you, right? Before that itself, the message is just like, I'm fine. And then that question comes, right? Somewhat scenario similar to this, isn't it? Or is
It's
it
like,
different? Like there we use vector clock to handle that.
I think here actually answer comes before the question, right? That's what it is.
Okay, yeah.
yeah,
Because
yeah, I mean, yeah, more or less, I mean, both of you are on the same page. It's just that they're trying to present the observer's perspective here and what happens when he is listening to this conversation, wherein he gets to hear this first and this later on. And the reason being is that is the lag that it has to propagate the message to its followers, I suppose. Mr. Poon says it here, it gets to partition leader 1, and then it goes to Mrs. Cake. And then parallelly, or maybe after this, it goes to the partition follower 1. So by the time it reaches here, this information reached before, because of the kind of distribution of the information over here. Okay. So clear to everyone. It's a matter of lag and the point which things get messed up. If some partitions are replicated slower than the others, an observer may see the answer before they see the question. Consistent prefix reads. This guarantee says that.
Yeah, it seems like he had some network problem. Let's give him a minute or two.
yeah, I think yes.
Yep.
Yes, sorry, I think my net kind of dropped it. Hope I'm audible. Yeah.
Yeah.
Okay.
It was like a monotonic read for you also, for us.
Okay.
Correct.
Yeah.
Okay. So yeah, consistent prefix reads basically they are ensuring that the sequence of write happen in a certain order and the same order is being read. Okay, that's the consistent prefix read. This is a particular problem in partition or sharded databases. Okay, and which we will discuss in chapter 6. If the database always applies writes in the same order, we will always see a consistent prefix. So this anomaly cannot happen. However, in many distributed databases, different partitions operate independently. So there is no global ordering of the writes. When a user reads from the database, they may see some part of the database in an older state and some in a newer state. One solution is to make sure that the writes are causally related to each other, are written the same partition. But in some applications that cannot be done efficiently. There are also algorithms that explicitly keep track of casual dependencies, the topic that we return to page 186. The happens before relationship and concurrency. Okay.
I think, yeah, I was about to say actually the WhatsApp messaging we said, right? So if we have a partitioning scheme based on the, let's say the user ID, then probably we'll see this issue. But actually, if you're going to partition the database based on the
Message ID.
Yeah, message ID or the group chat, right? a group chat, actually, if we are sharding based on that group chat ID, then actually everything goes to the same partition and everything will be ordered, I guess.
So if the, let's say if in a group folks from different regions are there, right? Asia, US, I mean, what is it? Pacific region, right? So like, then in that case, how do we shard it based on the region, or how? Or like, would it be shard?
Shard based on the group ID or the chat ID. So let's say we are creating a group. That group has an ID that is used to shard. Then we replicate to multiple places on the different geographies. Because actually yeah.
So in a group, folks from different regions, one from India, one from US. So first you shard it based on the group ID, right?
Yeah.
And then you replicate across India and US both, right?
So the thing to consider here, right? Actually, to have this ordering, right? All rights has to come to this one place. Let's say the master is in Europe, then all rights from all parts of the world should come to the master database in Europe. But actually, reads can happen from nearby replication. Yeah. That way, the ordering is there. Also, normally the access pattern is actually because when I load, actually, I want to fetch all the conversation for the groups I am part of, right?
Correct. Yes.
Yeah. So that will be then I have to find all the groups and I'll fetch that. Yeah.
So if one person is a member of let's say many groups, right? Let's say 100 groups are there.
Yeah.
So in that case, and what do you say? And as you said, that master is present in the Europe, right? So all the rights will go to the Europe of all the groups there itself, right?
Yeah, so that is a bad design, right? Actually, because the master. So let's say we have 3 data centers: one in Europe, one in Asia, and one in US, right? So we can split the load, the write load between all 3. Let's say the first group created the master is in Asia. For the second group created, so basically load balancing the rights
across the masters.
Across the masters. But actually, these databases, let's say the Europe is the master for the group chat ID 1, but actually the other 2 are the replicas for the group chat ID 1, right? You see. So each data center database will be the master for something and replica for something else. Because we have only 3 data centers, we have to put everything replica and the master into all these 3 databases.
Okay. But then the person who's sitting far away from that master, won't it be, I mean, his message will have a latency to reach to the master, right? Compared to the one,
exactly,
the guy sitting itself.
Because actually right now we are optimizing for the read path. So the read should be fast, the write will take a hit.
In this case, yeah.
Yeah.
So yeah, go ahead.
Yeah, normally these kind of websites, right, like the social media websites, actually all these guys are doing similar. Their writes go to one place, but actually they are all optimized for the read path. Read should be fast, actually.
So reads are replicated across the local regions, right? Whichever side that person belongs to. But the master will be.
Okay. Master could be in a different area.
Yeah, makes sense. So the ordering will happen at the master itself, right? Let's say 4 members are there. Somebody asked, how are you, right? The third person said, I'm fine, right? So the ordering will happen there itself at the master. And then they will delegate his message to the other person, right?
Yeah. So we have another option, right? Let's say we are going to use leaderless replication, right? So we all connect to our close by data centers. Right now, normally Cassandra. So when there is a conflict, right? I and you are gonna send the message at almost the same time, right? To the same shard, right? Because actually we are writing to the same shard, but now it's a concurrent write, right?
True. Yeah.
There is concurrency. The Cassandra uses the last writer wins policy, right?
LWW, yes. Last write wins.
probably one of our writes will be dropped.
Will be overwritten.
Yeah, that is for leader race, right? But for
No,
here,
no,
as you,
not for the leaderless, right?
yeah, leaderless, I mean to
Yep.
say. But
Yes.
for here, if you see, as you said, it will have different geographies will have different servers or sharded. So based on the group ID. But then if a person in a region sends a write to that server, okay, and that follower which is in a different region is lagging.
Mhm.
So then there will be an ordering issue, isn't it? Because someone actually replies to it, and this current server is not lagging.
So what happens is actually, my writes are going to, this is leaderless, right? Like Cassandra, my writes are going to somewhere in Europe, and yours is going to somewhere in the US, right? So both masters will accept your write, right? Now they're gonna replicate this. My write is going to the US data center. US data center looks at actually, okay, there is a conflict, right? At the same time, there are two writes for the same key. I don't know if I'm making sense or.
Yeah. So both the rights.
Yes.
I mean, both the rights will be transferred, right? I mean, what I'm trying to say, like one is writing to the master which is present in Europe, right? The other master is in US. Somebody is writing there, right? So the US, whatever, I mean, the master receives the data, he'll replicate it to the Europe master data. That is what you're saying.
Exactly, that conflict resolution box, right? That is where the problem, right?
But then why he wants to do that?
Because actually, because you want to see my messages too, right? Because you are reading and writing from your close by data center.
Correct. Yes.
So whatever I wrote to the channel should be sent to you in the WhatsApp chat.
Correct. So the nearest, yeah. So the master which is nearer to me, that will be will be replicated.
That person is responsible to put an order to the messages coming.
Yeah, makes sense. Yeah. Yep. Thank you. Yes, sir. Go ahead.
Okay. So cool. I mean, I'm gonna be most probably revisiting this part on chapter 6 because I couldn't quite get what prefix it's referring to. But nevertheless, let's go further. Then solutions. We're talking about solutions of how this lag can be addressed. When working with a eventually consistent system, it is worth thinking about how the application behaves. If the replication lag increases to several minutes or even hours, if the problem is my bad. If the answer is no problem, that's great. However, if the result is a bad experience for users, it's important to design a system to provide a stronger guarantee, such as a read after write. Pretending that the application is synchronous when in fact is asynchronous is a recipe for problems down the line. Okay. As discussed earlier, there are ways in which an application can provide a stronger guarantee with the underlying database. For example, by performing certain kinds of reads on the leader. However, dealing with these issues in application code is complex and easy to get wrong. It would be better if the application developers didn't have to worry about the subtle replication issues and could just trust the databases to do the right thing. This is why transactions exist. They are a way for a database to provide stronger guarantees so the application can be simpler. Single node transactions have existed for a long time. However, in the move to distributed, where we have replicated partitioned databases, many systems have abandoned them, claiming that transactions are too expensive in terms of performance and availability, and asserting that eventual consistency is inevitable in a scalable system. There is some truth in that statement, but it is overly simplistic, and we will develop a more nuanced view over the course of the rest of this book. We will return to the topic of the transactions in chapter 7 and 9, and we discuss some alternative mechanisms. Okay, I'm not so sure if there's anything to conclude here, but they're basically saying that there are approaches, but still doesn't work out. And very interesting point that they claim here is transactions are too expensive in terms of performance and availability, and asserting that eventual consistency is something that has to happen in scalable systems. So let's see. Anybody wishes to add some point here, or should we jump and go ahead?
No, I was thinking, right? Actually, he's talking about transactions. How does that help actually to preserve causality, right?
I think synchronization is what they do. It's
Mm,
more like making asynchronous, like a synchronous kind of a flow.
but
Transaction for replication, I think whenever some write is happening, it's when it is replicating across all the replicas.
actually, transaction means actually you provide atomicity, right? Actually, all or nothing,
Correct.
right? But actually here, the Mr. Poons and the other case, right? Actually, it is answer it is action by two different people, right? You cannot put that into a transaction, right? Actually, one person talks, as response to that, the other person says. So it is actually I don't think concept of transaction doesn't really apply. I don't know.
Yeah.
Yeah, that's fine. We can continue.
Okay, so let's say if we can always read from the leader, and it's also say we always read from the leader, it could be an issue. It's also easy to get wrong. How?
Yeah, that is the easiest solution, right? Then we lose the scalability part, right? And fault
Yeah,
scalability, right?
but this one is issue with the application. It's not like and it's getting wrong, meaning like, it's not get the right data, right?
Yeah, the ordering needs to be preserved. Yeah, I think so. Yeah. Yeah, I think yeah, that is one solution. Yes.
Yeah, but if we always read from the leader, then we always get the right data, right?
Yeah,
How
yeah.
could we get the wrong data?
No, if you read from but actually you have to read from the leader who wrote the data, right? Not the person who is close to me, right? Actually, if there is an ordering set by one person, then actually he has that data, right? In the correct order.
Yeah, but here say read after write. I mean, you read from the one that you write to, which is the leader.
Yeah, read your write consistency, reading from the master or where you wrote the master who wrote your data. That works actually. Yes. But then the problem is actually you may see you have to route. I don't know actually. So there is this confusion, right? The client has to know when I wrote the last data.
Okay. Yeah, I'm not sure. They say complex and easy you get wrong. How could it be complex if you read from the leader? Maybe something that
you basically you lose the scalability part, right? Or let's say the master is able to do, let's say 1,000 transactions per second, and you have multiple replicas. Still, actually, the replicas is sitting idle, right? We want to transfer the reads to the replicas. Then only we will get 3 times the read performance, right?
Yep.
yeah. But this one is like it's mainly about read after write. That means you write first.
Yeah, read after write we already solved earlier, right? With that transaction ID. So the reads doesn't need to go to the master. Reads can still go to the clients or to the replicas, but actually client needs to remember what is the last transaction ID I saw or I wrote.
I think there are different level of transaction, right? Like serializable is the one which can order anything, but at the cost of performance. Availability also, like everything has to be serialized. But then you have different levels of transaction you can choose from. I think depending on the use case, you can go for dirty read versus dirty write and all those levels and tune your application to do that. You still have to be like, depending on your use case, do some bookkeeping on as a like application developer. But like those are the knobs basically which transaction will allow you to do. Right? That's what I guess that's why they have brought transaction here, and maybe in the next transaction chapter they will go into the details.
Yeah, that are all good actually. If all the data you're writing stays within a shard, right? So across shards transactions, you should use two-phase commit or something.
Yes, and that is I think in transaction chapter they will go into the details.
Okay, cool.
Thanks.
And why does client needs to remember the last read what he has done?
Because otherwise, actually, let's say you connected to server and you saw the value of x is equal to 10. But actually, x was incremented from 1 to 10, right? So the next time you connected the last you're randomly getting connected to some replica, right? And the next replica you are connecting has a lag actually, right?
Yeah.
Now you saw the value. Now you again read the value of x. X goes back to 5.
Oh, that's an inconsistent in the yes.
Yeah, because at least I should see 10 actually. That's the requirement. I cannot see anything going back to 10. At least I should see the value of x as 10 because I know actually the 10 increment. Sorry, the value incremented from 1 to 10.
Yeah. But how do we know that the first time it got connected to the first server that was correct, like x equal to 10? That
No,
would
it
also
doesn't.
have been.
It doesn't matter, right? So whatever I saw last, from a client's perspective, that is the recent data. It may be a little old data, right? In the master, it will be x is equal to 12 now. But actually, as a client, whatever I saw x is equal to 10, that from a client's perspective, that is the recent data. Now that the wherever I read that data, that server crashed. Now I got reconnected to a different replica that has x is equal to 5. Now from the client's perspective, time is going back. It's not going forward.
Correct.
Yeah.
So that information the client will keep in its cache, right? What last time it has read, right?
Yeah, the transaction ID or some identifier for the last read.
Right.
Or maybe version or something.
Yeah, something version or something. Yeah.
But that cache can also be corrupted, right? In client, let's say it got corrupted.
Oh yeah, actually. So either two options are there, right? If this really matters for the client, then client has to store it in a persistent way that can survive crashes in a disk or somewhere. That's client's responsibility, right? That's not our responsibility. Server is only responsible that if you present me with a transaction ID, then I will make sure that you don't see anything before that transaction. Everything will be greater than or equal to that transaction ID.
Yeah, it makes sense also, right? Yeah. Why to show an old data? Yeah.
Cool. So I mean, from all that having said and done, I think so the solution that it has given here is that the read happening from the same replica. That's how they're going to be ensuring that at least the writer gets to read the same thing quickly. That's what I get. Okay. Yep. Now we move ahead. I hope everybody is clear. Anybody wishes to add? Okay, cool. Moving ahead. Multi-leader replication. So far in this chapter, we have only considered replication architectures using a single leader. Although there is a common approach, there are interesting alternatives. Leader-based replication has one major downside. There is only one leader, and all the writes must go through it. If you can't connect to the leader for any reason, for example, due to network interruption with the leader, you can't write to the database. A natural extension of the leader-based replication model is to allow more than one node to accept the writes. Replication still happens in the same way. Each node that processes a write must forward that data change to all the other nodes. We call this as a multi-leader configuration, also known as master-master or active-active replication. Okay. In this
So
setup,
for
each leader simultaneously. Yeah, go ahead.
So, I mean, one question, like for multi-leader, we should have only 2 leaders, right? Like if one fails, we don't need to do any election. The other will automatically become the master, right? So latency won't be there, right? But if let's say five master, if one goes down, there has to be election, right? Who would be the next master, or like automatically anyone will be assigned?
I think
Like by master.
what I was saying is actually multi-leader could be like a Cassandra right configuration. The other one is actually, I think for the MySQL we have the active mode, right? I think that also comes to the same multi-leader. If basically it's saying actually if 2 people are accepting the rights for the same key, then there is actually contention, and that is multi-leader. 2 or more actually.
2 or more than that.
Yeah.
Cassandra is a leaderless, right?
Sorry, say it again.
Cassandra is leaderless, right?
Yeah. I think actually, yeah, I think I'm getting confused here. It's multi-leader. Yeah, you're right. Actually, Cassandra doesn't come here. Actually, this is the master, I believe. Yeah.
Yeah.
Correct. Yeah.
Cassandra, Dynamo, all of them are leaderless. Yeah.
But everybody is a master.
Multi-leader is not a good way to do, isn't it? So, okay, let's see it. Yeah, go ahead. Yeah, sorry, Shashank, what was that?
No, I'm saying like in Cassandra, everybody is a leader only, right? Whosoever talks with the client, he becomes the leader, right?
No, they don't have that. They have that coordinator node and all those things.
Coordinator node.
Different one.
Yeah,
and then you have that yourself hinted and also. So that will come into picture. Yeah.
Okay. Just a correction, Santosh. So DynamoDB is not a leaderless.
No, not DynamoDB. Sorry, Dynamo.
There's no Dynamo system.
Yeah. So Dynamo, what they call that concept,
Okay.
As per that advanced. Yeah.
In reality, there is no Dynamo system.
Yeah, that is what you said last time also. Yeah. If we remember it.
Dynamo is earlier I used to think it's a product, but you mentioned that it's.
Yeah, I know that. I mean, people used to get confused.
So, but then DynamoDB is what? Is it a leader based?
It's a leader based system.
Okay, leader system. Okay. So, but only the name is the same breast. It doesn't use any of the concepts of Dynamo.
It use some concept.
But only the replication it doesn't use that way.
Yeah, but it's leader based. Yes, architecture is a little bit different, but it's follow some concepts from there.
Yeah, because the leader based architecture is completely different than leaderless, right? So based on that, the whole architecture of the application differs a lot, isn't it? Even if you see here now, based on leader, whatever the primary backup, whatever the model is, and whatever the issues we have are totally different than the issues what we have with the leaderless.
Yeah.
We don't have the same issues what we have with the primary backup.
Exactly.
The issue could be different, but maybe you can follow the concepts from the Dynamo paper to replicate your data. Some concepts you can follow from there.
I think the major issue is, yeah, go ahead.
I'm saying leaderless looks more fault tolerant and consistent, right? Like
maybe at least I slightly understood it better than the others, so therefore I think it also that way. Yeah.
See, in case of master, but if master fails, nobody can take. There has to be election, master will come. But in leaderless, if one of them fails, the other is there to take it up, right? I mean, those kind of things you don't see in the this leader replication. Or
because I think, yeah, what you say is right. Because Nick once mentioned that if you have a leader and if there is a leader election, you lose that connectivity for a minute or so. And that is more, and everything is unavailable. Yeah. So that doesn't happen in the leaderless, isn't it? So everything, at least someone is always present.
The other way to think about it, actually, if we are okay with losing data, then actually leaderless is fine, right? If you are absolutely sure we have to have all the data, then some strategy has to be there for the leaderless to handle the conflicts, right? The Dynamo paper is saying is actually it is presented to the user, but actually Cassandra uses the last writer wins. They have other ways to resolve it, but in a master, you're absolutely sure that there is no conflicts because master will solve it as soon as the rights come in.
Yeah, so everyone has his own challenges, and then we'll have to resolve that. Yeah.
And in leaderless, what was the even client helps to resolve it, right? The conflicts.
Yeah, that is offline, right? Actually, so as soon as it finds a conflict, either it has to call some callback handler to the client and ask him resolve it, please, right?
Correct.
But the applications for the leaderless seems to be, at least for the Dynamo, they are the very lightweight, like they talk about the shopping cart and all that stuff, right? But if you really want to do a heavy base applications, then I don't think so. Leaderless may be a really good way of doing it, because Cassandra also, the consistency has the tunable consistency. So you have to select. So you give all the options of the configuration to the user actually. So then everything goes to the user. So what he has to do. So that is slightly risky and tricky also, because if the user doesn't tune it, then you don't get the results what are expected. At least for the other systems, whenever we have the leader-based system, they are more relevant because the system handles everything for you. That is what I understand. Yeah, I don't know. Yeah. Yeah, it's flexibility, but at a cost, So the user has to be very intelligent enough to understand, and he has to do a lot of stuff.
Yeah, that is the topic. Yeah.
Okay.
So
Sorry. Yeah. Good, sir.
Go ahead.
Yep. Cool. So yep. So we're talking about the use cases. As in each setup, each leader simultaneously acts as a follower to other leaders. So use cases for multi-leader application. It rarely makes sense to use a multi-leader setup within a single data center, because the benefits rarely outweigh the added complexity. However, there are some situations in which this configuration is reasonable. Okay. So I think so. This statement quite heavily says that it's more to do with the multiple data centers rather than having it in a single data center setup. Okay. So multi-data center operation. Imagine you have a database with replicas in several different data centers, perhaps so that you can tolerate failure of an entire data center, or perhaps in order to be closer to your users. With a normal leader-based replication setup, the leader has to be in one of the data centers, and all writes must go through the data center. In a multi-leader configuration, you can have a leader in each data center, right? Figure 5.6, which is here. See, shows that the architecture might look like. Within each data center, a regular leader follow replication is used between the data centers. Each data center's leader replicates its changes to the leaders to other data centers. So this is the diagram, which is following a leader follower approach in one data center, and same thing with data center 2. At the same time, the leader replicates the changes to the other leader, but in a very via conflict resolution. So let's compare how the single leader and multi-leader configurations fare in a multi-data center deployment. Performance. In a single leader configuration, every write must go over the internet to the data center with the leader. This can add significant latency to writes and might contravene the purpose of having multiple data centers in the first place. In a multi-leader configuration, every write can be processed in the local data center and is replicated asynchronously to other data centers. Thus, the inter-data center network delay is hidden from the users, which means the perceived performance may be better. Right. Performance-wise, since it is getting replicated, it is consistent, be available on the other data centers. But for single, significant latency would come as it has to be read from that single leader of the data center. Then tolerance of data center outages. If a single leader configuration, if the data center with a leader fails, the failover can promote a follower in the another data center to be a leader. In a multi-leader configuration, each data center can continue operating independently of the others. The replication catches up when the failed data center comes back online. Okay. So normal scenario, the leader fails for the data center. The promotion happens. You can promote a follower in another data center to be a leader, right? Because this is a single leader model. Rest all of the data centers have followers. So one of the followers in the other data center becomes the leader. Right? That's the tolerance here. But in the multi-leader, that does not get impacted because every data center has a leader. And eventually, once the failed data center comes back online, it kind of takes the update. Tolerance of network problems. Traffic between data centers usually go over the public internet, which may be less reliable than the local network within a data center. A single leader configuration is very sensitive to problems in this inter-data center link because writes are made synchronously over the link. A multi-leader configuration with asynchronous replication can usually tolerate network problems better. A temporary network interruption does not prevent writes being processed. Okay. So from what I understand is that in a single leader configuration, writes are synchronously made over the link. So it has to wait for that to happen and then come back. Whereas a multi-leader configuration without synchronous replication can usually tolerate network better because a temporary network interruption does not prevent the write from being processed. So it's happening asynchronously. The update to the second leader. So it doesn't have to wait for the update to go back. That the write is still happening. The update goes back immediately. I hope that's what it means over here. In this case.
That makes sense. But at the same time, as a single leader, they could do the asynchronous over the link, right? So why, in this case, the single leader have to do the synchronous?
Because actually to provide fault tolerance, right? Let's say if everything is asynchronous, so let's say leader crashes, right? They have to bring up another leader, right? So if it's everything asynchronous, the next leader to be brought in will be lagging in writes. To avoid that, actually, at least one of them will be synchronously replicated. Rest of them will be asynchronously replicated.
This is more like that semi-synchronous
model. Yeah.
Cool.
That semi-synchronous way, yeah, okay.
I hope everybody is getting it till here. Anyone not getting anything, please highlight. We will discuss. Okay. Okay. I'm going to thought Shashank was saying something. All right.
No. I'm saying, do you want to continue or like next day?
We'll wrap it at least in this part.
Okay, sure. Let's finish.
Yeah, let's finish it till here. Some databases support multi-leader configurations by default, but it is also often implemented with external tools such as Tungsten Replicator for MySQL, BDR for PostgreSQL, and Golden Gate for Oracle. Yeah, this is interesting. Although multi-leader replication has advantages, it also has a big downside. The downside is what is the downside? The same data may be concurrently modified into different data centers. Right. Interesting. So there could be a data that's modified at two different data centers, and those write conflicts must be resolved indicated as the conflict resolution. And obviously there's a subsequent area where they're going to tackle this information. But as a multi-leader application is somewhat retrofitted feature. Sorry, in many databases, there are often subtle configuration pitfalls and surprising interactions with other database features. For example, auto-incremental keys, triggers, integrity constraints can be problematic. For this reason, multi-leader applications often considered dangerous territory that should be avoided if possible. Well, that's an interesting take.
Yeah, so see, if they say that statement, like the last one, what you read. So if they say that statement and then still they say MySQL having some tool, external tool to do that. So it means it is being used somewhere at least, right?
Yeah, it is getting used.
So then, so what is the real need, and as what is the real way they actually take into account all these issues and how they some way avoid these issues, or the applications whatever are being designed they ignore the issues, or they are fine with whatever the multi-leader issues are about what we discussed earlier.
Yeah, I think that's the reason.
Okay.
I know I have used Golden Gate before, but I was not fully involved in it. But so there were a lot of issues at that time actually.
Mm-hmm. So these tools are still popular, all of them?
Yeah, Golden Gate is heavily used actually in Oracle world.
Okay. Maybe it's used only for a small isolated region, not across the geography.
I think so, yeah.
Mm-hmm.
Oh, yeah, one good example for this multi-leader, right? Let's say we have the collaborative editing, right? You can think that as a multi-leader application. We both are working on the Google Docs, right? So each browser in our end actually is a master taking writes. Then it is sending that writes to the next browser. There somewhere in between, somewhere actually this conflict has to be resolved.
Oh yeah, that makes sense. So because even the load is not heavy in that case because it's distributed, right? So many users are not exactly modifying a particular line or a particular word at the same time.
Now think about that, right? Actually, we five people are exactly typing, correcting that word, right?
Mm-hmm.
So now how do we resolve that, right?
Mm-hmm.
So that is the challenge actually. I think there are some data structures like the conflict-free CRDTs or something. I think Redis implemented some of it. So they use actually that data structures for some these kind of configurations.
Mm-hmm. Yeah, I'm to see like 5 or 6 or maybe even hundreds of users doing the same thing at the same time. Those events are still manageable, instead of having like 100,000 users.
Now, if we all are editing to the same side, right? Actually, each browser will get every other's edit, right?
Yeah.
Now it has to merge it. So we should have a smart way to merge it. Otherwise, everything is a conflict.
Yeah, makes sense. Yeah, so it's very implementation dependent, isn't it? Sorry, go ahead.
No, I was just thinking that maybe multi-leader application makes sense when you are pushing the data specific to your profile or specific to your area, and you know that you are making the changes and you get to see that update immediately because it's the closest data center of yours. And then subsequently the other data centers get replicated with this information asynchronously.
Basically, you are sticking some users to one particular data center, right?
Yeah, I mean, mostly from a geographically distributed latency, they would be kind of hitting that data center closer to them.
But that has other issues, right? Actually, if Asia region is my home data center, if I travel to Europe, then Europe will be my home data center, right? Now, if I edit something Or let's say actually we both have actually yeah, because what I was trying to say is actually the conflict still can happen, right? Meaning if two people are editing the same page from two different data centers, we have a common website, and you are editing from the Europe region, I am editing from the Asia region, right? Both our rights will go to our nearest data center.
Right. It's more like putting comments maybe on a particular area.
Exactly.
Common area. That's what I'm saying. This is definitely a problem scenario for common area changes. But I think so. This, I mean, I was looking from use cases where multi-leader is beneficial. Vice versa. So I was just thinking that maybe it is useful from a individual changes perspective. Like I'm pushing a YouTube video, from my end. So it's kind of going through that one DC which is closer to me. Eventually, others don't get to see it, obviously, till the update happens. But I know it's getting updated, and immediately I get to know that it's updated. And subsequently, asynchronously, the replication happens to the other DCs. So, that way, high availability scenarios, eventual consistency, high availability. I think so. I was kind of trying to fit that situation for multi-leader configuration.
That's pretty much the leaderless, right?
Somewhere they actually.
Sorry, go ahead, Santosh.
No, somewhere they actually, try to cross each other's boundaries, right? At least the conceptual wise, yeah.
In this multi-leader, is it like they work? I know they work independently, but is it work like the same time we talked before? Like we have in this case we have single document ID, and this leader will take care of this document ID only. So it doesn't matter who where people is. They always to go to that leader when they want to update this document ID. Is that still multi-leader?
No, right? Because then your rights will always go to one data center, no matter where you are in the world, right?
Yes, but I have all the data center for different document ID.
So say it again. Last thing you said.
So all the data centers can take care of different document ID.
Different document ID, then it's fine, I guess, right? So if we are writing to the same key, then only we have the problem, right?
But then even if it's a different document ID, I think so. The whole idea of a leader-follower concept is that the write will happen on the leader first, and then it gets propagated to the followers. So if I'm trying to imagine the leader-follower scenario in a data center kind of a perspective, one data center has a leader in it. The rest of them are the followers. So I mean, essentially, it means that all the DCs where I'm writing something, it has to go to the leader DC first, have that updated over there, and then propagated to the followers in the follower DCs. If a single, leader follower situation is to be imagined.
Yeah.
Something like a chain
it would be less conflict, I think.
Yeah. I think it's more subjective to the utility, right? It's more, I think so design-wise, we have the capability to design it the way we want to, but it all comes down to what is the utility. If we are looking at something atomic, maybe then a single leader follower concept kind of helps. But if we know that consistency can be compromised, availability is a concern, we can have multi-leader configuration in place so that everybody gets quickly get the updates, even though some might be lagging behind, but some at least get the updates in a multi-leader scenario.
Yep. No problem. So I think Shashank, Moses, you want to end over here, right?
We can call more.
Yes, we can end here. Yep.
Let's
Cool.
park it for today, and then
Yep.
Thank
All right.
you,
Thank you so
Moses.
much.